everyone for being here. I'm really happy to see so many faces here, especially with such a specific topic about particle physics. Yeah, you might be wondering why particle physics on a Dutch Innovation Days. Well, besides the fact that actually a lot of innovation have come from particle physics in the past, the Dutch Innovation Days is also a festival of ideas and broadening your horizon. And in the next 20 minutes, I hope to give you, make you aware of a world that you might not have been aware of before, and that can inspire you. Yeah, and don't worry, it won't be a particle physics lecture that I'm giving here. I'll try to keep it low level and accessible for everyone. So I called the talk "Discover the World You Cannot See with Bare Eyes." And I'm having one slide about my personal research, just as a quick introduction. So I'm doing my PhD research at the detector, which is called KM3net, and it stands for Cubic Kilometer Neutrino Telescope. Now, if you hear telescope, you might think of something to look through to the sky. But in fact, this is a telescope, a detector that we're building at the bottom of the Mediterranean Sea, 3 kilometers depth. It's going to be huge, because it's going to be cubic kilometers, so kilometer by kilometer by kilometer, to detect fundamental particles that are originally coming from objects in the sky, like stars exploding or something, among other things. A banana also emits neutrinos, but that's a side note. So it really connects how the smallest particles can teach us about the biggest things, and that's also how I kind of set up this talk. So I'll cover 3 different scales: the smallest particles, the world as we think we know it, and the world of the biggest scales. And we do that by means of a fact and a fable. So you should all have gotten a red and a green card. So I'll have some statements for you and check yeah, your knowledge. So let's do a quick practice. Who had physics in high school? Okay, 50-50. Who had physics in their exam year at high school? More red cards. Okay, who liked physics? Who thinks I'm a typical physicist? Stereotypes. Yeah, all right, so I think you found the cards. Let's now go to the smallest building blocks of nature. So particle physics really comes down to the following. We live here on Earth, and we designed it to our wishes, to our needs. We designed it quite nicely, I think, making use of a lot of different materials in different forms, liquid, solid, whatever. Now take, for example, this crystal. If you break that crystal into half, and you break that half into half, and you break that unable to, can you continue forever? Or is there a point where it's unable to divide what you have left into smaller parts? In other words, are there undividable building blocks of nature? That is really the question of particle physics. And yeah, you may ask, what are these fundamental particles if they exist? What are the interactions between them? What are the forces between them? Now, I'm going to show you one formula, and I promise it's the only formula I'll show you today, but it's going to be a big one. And I'm going to ask you a question about it. So the question is, this single formula describes, 1, which particles exist, and whether particles have mass, and through which interactions they may interact with each other, and it describes all observed type of forces. Now I want to see your cards. Is this true or is this false? False, 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 true, true, true. The answer is it's false. And that is because, in fact, the first 3 are actually true, but the last thing that I put down is not true. So particle physics is really basically this single formula. And it really describes, it's a mathematical description of a physical system. So it really describes, we know, well, the particles that we know. So in purple and green, we have all matter particles that we know. In red, we have the forces between them. And then in yellow, we have the Higgs particle giving them all mass. And it's really a big triumph of modern particle physics. And it's an interplay between theory and experiment. So the formula is theory. And then based on the formula, you can make predictions. And then with these predictions, you can, well, build an experiment to test the predictions and see whether it's true or not. And often we confirm the theory, that's why the theory is so good, but there are also examples where we know that there are gaps in the theory, and then because we observe something else, or the theory doesn't describe what we observe. And then the theorists have to go back to the drawing table and try again and improve the model. So one very important thing that is lacking on this model, and that's also why the previous statement was false, is that there is no gravity in the whole. Whereas actually, we cannot describe gravity with this model. Whereas actually, gravity is the type of force you might think we know best, but actually it's the type of force we know worst. I'm sure you know what happens if we put a bowling ball and a couple of feathers in a head. We could have done it here in the church, and we drop it. I'm sure you know that the bowling ball falls fastest towards the earth. But actually, I doubt whether you really understand gravity, because what happens if we do the same experiment in a vacuum chamber? So this is really a video, and you can see that they fall with exactly the same speed. And this is because the Earth is pulling to the other object. It's really masses attracting to each other, and the mass of the Earth is so much bigger than the mass of the feathers and the mass of the bowling ball that it doesn't really matter. The small mass difference between the bowling ball and the feathers is neglectable. It's really the air resistance that, shows us the way we think we know gravity, but it's actually air resistance that we're dealing with. So, let's go back to the particle physics, and then from these 12 purple and green matter particles, my personal research is on these 3 neutrino particles, and they're often referred to as ghost particles. And now my next question to you is, neutrinos are called ghost particles because they can fly straight through normal matter. Is this true or false? I see many, well, 50-50, I think. So this is a fact. So neutrinos are indeed particles that can fly through matter. And they are with many. So, for example, if you look at your thumbnail, which is approximately a square centimeter, every second, 65 billion neutrinos pass through it, just from the sun. So every second, 65 billion neutrinos pass through every square centimeter, straight through the Earth, straight through our body. We don't notice it, but it happens. And to detect these particles, we're building a detector. Now, this is all particle physics that you might not have heard of before. What you might have, or actually it's which is a particle accelerator. It's a huge accelerator, or actually it's a particle physics laboratory in Geneva and established in 1954. And one of the experiments they're doing there is the LHC, the Large Hadron Collider, which is this 27-kilometer underground tunnel in which they accelerate particles, they smash them to each other, they look at what comes out of it, and basically what they try to do is confirm this huge formula or find the gaps in where our knowledge is lacking. So my next question about CERN, in this case, is particle accelerators, or well, related to CERN, particle accelerators are also found in hospitals. Is this a fact or a fable? Many green cards, some red ones. This is a fact. So actually, particle acceleration is really used, in this case, for cancer treatment. Here, it's not a circular accelerator, but a linear accelerator, but it's exactly the same principle of accelerating particles, and our knowledge about particle physics has helped us to use these particles, in this case, to kind of damage the cancer cells while keeping the tissue around it as healthy as possible. And there are many, many, many more innovations that have come from fundamental particle physics, in this case, for example, at CERN. Some more examples are the first PET scan. So PET scan is to basically find where the cancer is, for example, among other things. The first World Wide Web was created at CERN. It was just to kind of exchange information among computers, among physicists, among countries. Antimatter is used against cancer. And a very recent development is that they now also, again, using pixels developed at CERN, to be able to make a 3D colored X-ray image that could also, in the future, really help in hospitals for doctors to locate problems and to, well, better cure the people. So now this was the world of the smallest particles. Let's now go to the biggest scales, and maybe beyond. Because we humans can accelerate particles to huge amount of and huge speeds, almost the speed of light. But the universe is way better at this. So here what I show is an active galactic nuclei, which is basically a whole galaxy with a black hole inside. And this black hole is kind of eating its own matter from the galaxy and spitting it out into particle beams in which particles get huge amount of energies. Energies 200 million times more than we are able to create in CERN, in the CERN experiment. Now the next question I have for you is, if you accelerate particles infinitely long, they will get an infinitely high speed. Many red cards, a couple of green ones. This is a fable, because nothing can go faster than light. So it's impossible to give something a speed that is faster than light. And the speed of light is 300,000 kilometers per second. And also, if you would be able to go faster than light, you'll definitely win the Nobel Prize and you'll be able to time travel. But I won't go into details. So this is a very nice illustration of the speed of light. It shows how fast the speed of light is. So every second, a light can travel 7.5 times around the Earth. At the same time, on cosmological scales, the speed of light is not actually that fast. So here I show the Earth with the moon next to it, and here we have Mars, the closest planet on the outside of the Earth. And if they are on closest approach, here you can see how fast light is traveling, which is actually not that fast at all at cosmological scales. So it takes light 3 minutes to go from Earth to Mars. Also, light from the sun, when we see it, it's already 8 minutes out. It took 8 minutes to get from the sun to our eyes. So if the sun would go out, which is not something realistic, but we will notice it only 8 minutes later by means of visual observation. So, and the fact that, maybe I should go back one slide. So the fact that nothing can go faster than light is one of the postulates from Albert Einstein, his special theory of relativity. And that brings me to the next question for you. So my question is, without Einstein's theory of relativity, we would not be able to properly navigate with Google Maps. Is this true or false? You really give mixed answers. I like it. This is a fact. And what I would like to illustrate with this is that you definitely not always know the purpose of some physical theory when you came up with it. So, because if we would have asked Albert Einstein when he came up with his theory, what is the use of this? Why should we know about this theory? Who cares? How does it impact our lives? He would have never answered such that you could use Google Maps on your phone every day to find your way around. But without his theory of relativity, we would not have the proper corrections needed for the satellites to position you on Earth. And therefore, you will be meters off, and whole navigation would be useless. So now the last scale that I'll talk about is the world as we think we know it. And that relates a little bit more to the detector that I work at. So remember, we are building a detector at the bottom of that can fly through everything to detect subatomic particles, namely the neutrinos, that can fly through everything. So you have to be clever to measure them, because they will also fly straight through your detector. And for my personal research, these neutrinos are coming from a cosmological object. Now, I don't know if you paid attention when you walked into the church, but I think you've seen the tower, which is approximately 60 meters high. So my question is, the detector will be more than 10 times the tower of this church tall. Is this a fact or a fable? All right, mixed again. So if you paid very well attention, the tower is 60 meters. The detector will be approximately a kilometer. In fact, this will be 700 meters. But that means you'll have to put 10 times this tower on top of each other to get the height of the detector. So I invite you, if you go out of the church, look back, imagine 10 times the tower on top of each other, and that's basically the length of one of the strings that makes this network of optical modules to detect the neutrinos. So it's really going to be huge. And to show it, well, I don't know if you can see it with this light, but the detector is basically here with the Eiffel Tower put next to it. Here is the church that we're in, and this is, I didn't say it, but actually we're building 2 detectors. And I obviously was referring to the big one, but we're also building a smaller one, one in Italy, the big one in Italy, and the small one in France. And the smaller one is this one with the Tower of Pisa next to it. So it's really going to be huge. And the footprint will cover much more than the center of Enschede. So just to give you an idea of how big this detector is going to be. Now, my last question I have for you is, well, actually, let me give a quick introduction, because it will be a network of lines, as said, with these optical modules. So they basically have some eyes. These are kind of very light-sensitive eyes. These modules are approximately this size, and they can detect light. And we're building them all by hand. Most of the components that we need for this detector are especially designed for this detector, because yeah, you want something crazy that does not exist. You want a detector at 3 kilometers depth to detect single photons, in this case. So everything is basically man-made. You cannot go to an industry and ask, can we order this detector? You have to invent it yourself. And that's why there's also so much innovation coming from fundamental research. So basically we make these modules all by hand, and we do it in halves. And then we put the 2 halves together. And now my question to you is, we don't need to glue the 2 half glass spheres, because underwater pressure will keep the 2 halves together. Is this a fact or a fable? It's a fact. So I find it super cool, but the glass spheres, they have to be obviously very thin and precisely shaped. How do you say it? And so, but then once they fit together quite well, it's actually, there is a huge pressure underwater. So the pressure makes sure that the 2 halves stay together, and we don't necessarily need to glue it. We do put something around it just in case, but it's actually not necessary. And well, yeah, that's basically were all the questions I had for you. So yeah, I think fundamental particle physics, and actually in general fundamental physics, doesn't always seem to be useful. It's really fundamental research, just gaining knowledge, just being curious, try to understand the world around you, and where we don't understand it, dive into it. And yeah, that's basically really the dream of the physicists they have. And just to reach that goal, they need innovations, and they need the best pixels, the fastest sensors, the most accurate precision, and therefore they need to design their own and innovate, in fact, their own techniques sometimes. So my take-home message for you is be curious, because thanks to curiosity, it's that we make discoveries. And did you live in the world as we know it today, with the precious technologies and the knowledge that we have? And I think innovation will follow kind of automatically from that, even though it may not always seem obvious. And with that, I would like to thank you.